Hey everybody, welcome to the Pipeline Integrity Show. I'm your host, Hussain Fadhel. We just finished off a wonderful interview with Colin Scott where we discussed crack assessment models as well as his new model, the Gamma Exponent model. Hope you enjoy this interview and see you soon. Hey everybody, welcome back to the Pipeline Integrity Show. I'm here again, part 2 with Colin Scott, where we're going to be talking about the Gamma Exponent model. Colin, welcome back.
Thank you very much. I appreciate the chance to talk to you again. I think we covered some pretty good ground yesterday and hopefully more to come.
Perfect. So why don't we start off with, if you could walk us through the history of crack management and, maybe a bit of a summary from yesterday, but just a bit of a holistic statement on the evolution of how crack management started and where it is today.
Okay, sure. So for those of you that weren't around for the previous talk, my name is Colin Scott. I'm a pipeline integrity engineer based here in Calgary. I've got degrees from Queen's University and McMaster University, and it's when I was in graduate school when I got involved in fracture mechanics. Now, we talked yesterday that there are several different fracture mechanics models that are available to the pipeline industry in order to look after crack management projects. And we kind of came up with 3 different buckets. There's the 𝐂𝐫𝐚𝐜 bucket, which includes the 𝐂𝐫𝐚𝐜 model for through-wall cracks, which you would use for a leak rupture boundary assessment. There's the original 𝐂𝐫𝐚𝐜 model that you would use for a surface breaking crack. There's a modified 𝐂𝐫𝐚𝐜 model that tries to improve on some of the problems from the original. So you've got three models there in the 𝐂𝐫𝐚𝐜 bucket. And then we also talked that there are probably 3 models or maybe more that fall into the bucket of failure assessment diagrams. So those are things like API 579, British Standard 7910, and then the new model that came out of PRCI called the MAT8 model. And with those, you're looking at a brittle fracture type calculation and a ductile fracture type calculation, and you're trying to satisfy both of those to make sure your cracks are safe. The third bucket is 𝐶ORLAS. 𝐶ORLAS is kind of a standalone model that works differently from the other ones. It's actually got 2 models buried into it. One is a flow strength based model, which is essentially like ASME B31G. And then the other one is a fracture based model, which takes into account the toughness of the material. And with 𝐶ORLAS, you actually do both calculations and you just choose the lower bound value in order to be conservative. So there really are a lot of choices for the pipeline industry out there. The operators tend to gravitate towards some for some reasons and away from others for other reasons. Now, what I mentioned yesterday is that I've been really looking into the derivation of the 𝐂𝐫𝐚𝐜 models, and I've got a couple of things that really make me scratch my head. And so it's kind of put me on a path towards trying to understand how those derivations were done, and then where I see that there are some mathematical and theoretical failings, and then I'm trying to fix it. So as you mentioned, I've come up with something called the Gamma Exponent model that I'm gonna introduce you to today. Now, when it comes to the history of fracture mechanics that's really pertinent to this issue, you have to go back to the early 1960s. There were a couple of researchers named Dugdale and Barenblatt. And Dugdale and Barenblatt were working with linear elastic fracture mechanics, which was a relatively recently invented thing. And what they were trying to do is they were trying to simulate elastic plastic behavior. And what they did is they came up with something called the strip yield solution, where they said, you imagine that you have a sheet of material, it has a through crack in it, you're applying a stress to that sheet of material. Can you figure out what is the stress intensity factor at the tip of that through wall crack, and taking into account that there's some elastic plastic behavior. So that's kind of the first thing is the strip yield model solution. And it's a classic piece of work. I agree with it completely. Also in the 1960s, there was, I believe it was a graduate student, it could have been a postdoc researcher, a fellow named Folius. And what Folius was doing is he was using elasticity theory to try and figure out what is the stress concentration at the end of a through wall crack in a curved surface. So again, he's got a through wall crack. He was looking at both spheres and cylinders. So we now have 2 things that are very heavily based on length because they are associated with through wall cracks. Okay. From those 2 starting points, we jump to, there was a group in Columbus, Ohio at the Battelle Institute, and they're generally known as the NG18 committee. and they were doing some really seminal pipeline engineering work in the late 60s and early 1970s. I actually looked up NG18 thinking it meant like natural gas, you know, group number 18, nothing to do with anything. But they came up with something that has really got me scratching my head. And so I'm gonna explain it a little bit, and then I'll jump back over to a slide just to show you the mathematics of it. What they did is they came up with an empirical model where they knew that they had a Folius factor, which would calculate the stress concentration associated with the depth, with the length. But then they needed a model to account for depth in the case of a surface breaking flaw. So they came up with a very, very simple ratio. And what I'm going to do right now, if I can, is I'm just going to pop my screen over and just give you a little idea of the mathematics. I think it's easier if people can just look at the math and have a sense of what's going on. Okay, so this is basically what I've nicknamed the basic NG18 equation. So this is, from what I can tell, this is an empirical equation that was developed in the late 1960s. I have not seen a mathematical derivation, and I really don't think that there is one, because what's interesting with this is they have a depth component here, and they also have a length component, kind of both together in kind of an unusual way. Now, you see on the left-hand side, we've got this ratio, strength, predicted failure strength divided by the flow strength. So typically that term is nicknamed the remaining strength. And then on the right side of the equation, we have a fraction where the top of it is 1 minus d over t, where d over t is the flaw depth ratio. So the depth of either a corrosion or cracking flaw divided by the wall thickness. And then that's all on top of 1 minus 1 over m d over t. And m here is the Folius factor that I just mentioned. So you'll see that down there at the bottom. M is a function of the z parameter, and the z parameter is defined as the length squared divided by the diameter and the wall thickness. So basically, if you have a very, very short crack, your m factor, your Folius factor will be close to 1, meaning that you really just have a one-time magnification of your stress. But as you get a longer and longer flaw, that Folius factor will go to 2 or 3 or 4 or 5. And that has a big effect on your basic NG18 equation. So a lot of people should be familiar with this, particularly if they're in the corrosion business, because this is the basis of 𝐂𝐫𝐵 B31G. Now, if you look at those models, they'll typically have other factors in there. So original B31G has a 2/3 factor, and modified B31G has got a 0.85 factor, but essentially this is just the bare bones of it. So I'm hoping that your viewers will be somewhat familiar with that.
Yeah, I think anyone who uses the corrosion models will recognize this right away.
Yeah. Okay, so I think that's the only slide I need to show you right now. So I'm just going to hit the stop share button, and hopefully we're back to where we started. And there we are. Okay, so here we're at the point where in the 1960s, they're basically, I've described three separate models. One is the strip yield model, one is the Folius factor, and one is the NG18 equation that I've just showed you. Now, if you think about it, all of those are based on through wall cracks, right? And because they're based on through wall cracks, they're based on length. Now, I think a really, really good step that the NG18 committee did to start off all of their work in the 70s was to come up with a through wall crack assessment model. So that's where they're looking at a leak rupture boundary. So what they did is they took the strip yield model, which is based on length, and they took the Folius factor, which is based on length, put them together. Very, very good model. If you look at the validation, all the data points are right on the money. Plus or minus is about 10%, which is really, really fantastic. So that, I think, was very, very good work. Now, the next thing that happened, or it was probably all concurrent, was that basic NG18 equation was turned into 𝐂𝐫𝐵 B31G, which is used for a surface flaw. And there was a whole series of corrosion failure hydro tests done in the lab. And if you look at a correlation between all those corrosion flaw tests against the NG18 equation, you'll find it's about 30% overly conservative. You know, that's quite a lot when you think about it. When you think about the regulations of our pipeline and how we design our pipelines, we automatically put here in Canada, we would put on a 25% safety factor, right? Because we're always designing, or typically designing, to an 80% SMISE. So to add another 30% conservatism, that's quite a lot. And to my knowledge, nobody that was involved in that work ever really came up with a rationale as to why would it be so overly conservative. Now, my personal feeling is that when you look at that NG18 equation, you've got the 1 over dt term, which is based on depth, which is what you want for a surface breaking flaw. But then you've also got this Folies factor, which is length, and length is really not super important. You're not worried about your flaw getting longer, so why are you worried so much about the stress concentration associated with getting longer? There should be more focus on the depth, in my mind. So when I see the NG18 equation, I say to myself, well, mathematically, it's not lined up properly. It's kind of wonky. There's too much mathematical focus being put on the length, and maybe not as much being put on the depth, and it's just completely out of balance. And because of that, all those numbers kind of get swung over by about 30%. Now that 30% is very expensive for the industry, if you think about it. Some of the larger companies are probably spending several $100 million a year on their dig program. And to know that there's an unexplained 30% there, that's a couple of $100 million. So I kind of have reservations right there about that. Now, the second thing that, or the next thing that the NG18 committee was doing was they were also looking at cracks, not just corrosion, but cracks. And so what they did there is they took the NG18 equation, so B31G, and then they took the strip yield model, which, as we mentioned, that's based on through wall cracks. They Frankensteined the whole thing together. So again, we have a model that is very, very strongly mathematically and theoretically focused on length, which we're looking at the wrong direction here. If you look at the 𝐂𝐫𝐚𝐜 model, the original 𝐂𝐫𝐚𝐜 model, my numbers show, is about 10 or 15% overly conservative, which is really not too bad. And my suspicion is, and this is just my speculation, is that the analysts that were doing this work came up with the approach, they Frankensteined those two models together, their data came out pretty good, and they had no reason to think that there was anything, fundamentally wrong. I mean, you wouldn't. You're pretty close. You'll look to fine tune a few assumptions here and there, but you're not going to say to yourself, I have a length and depth problem, right? Typically. So that's kind of where that stands. Now, if you look at the NG18 equation and the strip yield model and the Folies factor, those sort of three components have also landed in the failure assessment diagram models. So you know from your failure assessment diagrams that you've got a y-axis, which looks at brittle fracture, and you've got an x-axis, which looks at ductile fracture. And if you look at that ductile fracture component, it's pretty darn likely that the industry standards you're using is going to have some sort of variation of the NG18 equations. And so that means it's very heavily based on length rather than depth. The second thing is, when you look at that curved limit on top of your failure assessment diagram, my understanding is that that's also based on a strip yield solution, which is based on length. So you've kind of sort of got a double whammy there. Your failure assessment diagrams are very heavily based on length rather than depth, and they become very, very conservative as well. We talked a little bit yesterday about the conservatism in different models, and if you look at something like API 579, I've seen some studies where you're potentially 30, 40, 50% overly conservative. In my mind, it's because you've got so much of your math is leaning on that length issue. When you look at 𝐶ORLAS, 𝐶ORLAS has two components. One is essentially B31G, though it's got a couple little correction factors in it, but that's based on length. And then the other one is the fracture mechanics model. So when you look at all of these different models that are working with surface breaking cracks or surface breaking corrosion, all of them are coming across as conservative, and all of them have that same real length focus in them. So that really had my head, kind of buzzing for a while and scratching my head and wondering, is this a better way to do it? So what I decided to do is, with the original 𝐂𝐫𝐚𝐜 model, essentially with that, you start with a through wall crack, you do all the math, and then you make a correction for depth.
So I have just one question.
Sure.
And maybe you explained it, but if you could explain a bit further, you're mentioning that they're focused on length and not on depth, and then you sort of mentioned that we're not sort of concerned with the crack getting longer. Can you explain why that is? Like, do cracks not grow lengthwise, or they just go depthwise? Is that the idea?
In very simple terms, yes. If you think about it, if we have a through-wall crack, you may have a short crack that acts as a leak. But then when you go through the math of the strip yield model solution and 𝐂𝐫𝐚𝐜, you're worried if that short crack that's leaking could potentially extend and rupture. That's really your key concern, right? But when you have a surface breaking crack, you're really worried about keeping your gas and keeping your oil in the pipe, right? So that means you're worried about your crack going through wall. You're worried about your crack extending through the depth, through the pipe wall, and causing either a leak or a rupture. If you have a surface crack that's getting longer, you're not going to lose over that. You're not going to lose a whole lot of sleep over that until it fails in the radial direction. So I have to admit that when you look at some of the studies that are done on stress corrosion cracking, some of those will study looking at how these cracks are growing in the length direction, but ultimately that's really just kind of looking ahead to how big a problem would you have if those cracks were to fail in the depth direction. If you look at something like fatigue, which is something we talked about quite a bit yesterday, you actually have to do a calculation to see how your crack is growing in the depth direction. And if you want to, you can do a crack growth calculation in the length direction. But typically, when you look at those different dimensions, your crack growth in the depth direction is probably going to be 10 times, 20 times, 50 times more than it is in the length direction. So typically, the length is something you don't really need to worry about. Now, if you've got an integrity program where you're going through a series of features and you're trying to figure out what's going to fail, you can figure out what's going to fail, and then perhaps as your consequence analysis in your risk management, for your consequence analysis, you might do a secondary calculation on leak rupture boundaries where you say to yourself, is this long enough to be a rupture, or is this short enough that it's just going to be a leak? Because that would have a big effect on your risk management kind of mentality. So that's my answer to that one.
Perfect. Thank you. Yep.
Okay, so I look back at the derivation of the original 𝐂𝐫𝐚𝐜 model, and I say to myself, well, rather than starting with a through-all crack of whatever length, and then coming up with kind of the NG18 equation correction factor for depth, why don't I redo that whole strip yield model solution starting with a part through wall crack? Assume I've got a plate with a long, infinitely long part through wall crack, and then go through all the mathematics exactly like they did 50 years ago with depth correction factors where I need them. And then at the end of all that, see if I need a correction for length. And so when you go through the fracture mechanics side of things, there are really three changes to what I did to the original strip yield solution. The first is, because I'm dealing with an edge crack, a surface crack, I typically put in a 1.12 correction factor on the stress intensity, right? So if you think back of your old college textbooks, that was one of the classic questions that you'd have. So you put in a 1.12 correction factor. The second thing is you use depth rather than length. And then the third thing is there's what's called a back wall correction factor, which means that as your crack grows deeper and deeper through the wall of the pipe, there's actually going to be a higher stress concentration as it gets closer and closer to that back wall. So I used a very simplistic term. It's the square root of secant of pi over 2 times the crack depth ratio. So basically, I redid the entire strip yield model solution with those three very simple changes. And what I found that was really, really interesting to me is that secant term that I put in there is kind of an unusual one. It's a little tricky to handle, but as I propagated it through my mathematical solution and twisted all the math and unfurled the whole thing, I actually popped up with a term that very, very closely relates to the original NG18 equation. So I didn't need to come up with a log secant model and NG18 equation and Frankenstein anything together. The way I developed my model, it kind of produced this natural equation. So I think that because the math is a big handful, well, not a big handful, a big handful to talk about, what I'm going to do is I'm going to jump back and I'm going to show you maybe, I've probably got 3 or 4 slides that outline the model, and I think we'll jump there and then we'll jump back and talk some more. Is that good?
Sure, yep.
Here we have my basic gamma exponent model. And what you'll notice about this thing, first of all, and I think that this is really important based on some of the things we talked about yesterday, is it's just a one-line equation, right? You don't need to buy $5,000 or $10,000 worth of software to work with an equation like this. You could type this into your spreadsheet in about 2 minutes and do a couple of checks and you'd be off and running. You don't need to look through a 1,000-page industry standard, bouncing up and down and all around. You don't need to look at endless pages of tables of crack depths, of crack lengths, of G factors, of all of that kind of nonsense. So anybody that's familiar with the original log secant model will kind of see a lot of similarities here. This is what I call the sort of the unfolded version. On the left-hand, starting from the left-hand side, we have remaining strength, which is the predicted failure strength over the flow strength, just like we have before in the other models. Then we go to a term which is 1 minus A over T. So 1 minus crack depth over the wall thickness. So that term is essentially just the remaining wall thickness. You know, how much material is there behind the crack? And that's to the gamma exponent. Then we've got a 2 over pi factor, an arc cos, and an exponential term, just like we would have in the log secant model. We have pi over k squared, where our k squared is going to be our material toughness. And then that's all on top of 10 times the crack depth times the flow strength squared. Now, you'll see at the bottom there, I've got the gamma exponent is defined as the minimum of 2c, which is the crack length, divided by the pipeline radius. But the maximum number that you can have for that is 1. And that's a very simplistic thing. Essentially what this gamma exponent is saying is, if your crack length is longer than the radius of the pipe, there's no more decrease in strength associated with that crack. Okay, so there's basically 3 changes here. I mentioned that there were 3 changes earlier, and how this manifests itself is, when you compare this to the original log secant model, you no longer have that NG18 B31G term. That's been switched out, and it's the remaining ligament to the gamma exponent. And that all comes out of the derivation of the back wall correction factor, which I found to be just a fantastic coincidence. Usually you would not have a 10 factor. Usually you would have an 8 factor in that exponential term. Now what's going on there is, if you take your edge crack stress intensity factor of 1.12, as you go through the math, that gets squared. So you get 1.12 times 1.12 times the typical 8 factor, and it rounds off to 10. It's actually like 10.2, but I think it's nice and easy to do it this way. So that's basically where the equation stands. Easy enough to type into your Excel spreadsheet. Now, just like all models, I do have some fine print. So I'm going to kind of walk you through some fine print, and then I'm going to show you how the validation works, and then we can sort of bounce back to the conversation.
Perfect. Yeah,
so
sounds good.
If I go to my next slide here, it's the fine print. The derivation I didn't actually account for curvature. It's essentially a flat plate solution. So I specify that you have to have thin wall pipe of D over T over 20. That's somewhat arbitrary, but it seems to be working so far. When it comes to flow strength, I've just used the yield strength plus 69 megapascals or yield strength plus the 10 KSI. That's pretty standard for most of the pipeline steels we use. There are some cases where other people will look at the higher strength steels and they'll come up with sort of average of yield strength and tensile strength, or 115% of the yield strength. I haven't played around with that. So far, this seems to be working fairly well. With the flaw depth, I can modify that by pi over 4 factor. So that's pretty standard in the fraction mechanics business. Essentially, pi over 4, you're approximating the semi-elliptical profile of the crack, and that mathematically, geometrically turns out to be the average depth along the crack front. So what I'll do is I'll use that for any of my fatigue cracks because I expect some curvature in them. I will use that for any stress corrosion cracks. Again, you know, you get that crack growth in the depth direction, there's going to be a little curvature there. And then if I have a corrosion flaw in which I don't have a complete profile, I make this simplification that I don't think that corrosion flaw is going to be a sharp, like rectangular box of corrosion. I'm going to assume it's going to have some curvature in it. So I'll use the pi over 4 there. I have been working on a level 2 algorithm, which I call the 𝐂𝐫𝐚. It's kind of my equivalent of R-string. I'm not going to tell you exactly how it works right now. I'm trying to publish that through a NACE paper. So you'll just have to sit tight on getting the math on that. It's a little bit like R-string, but there are a couple of key differences that come out of just the nature of this model being a little bit different. I validated that on metal loss flaws, but not on cracks yet. Another thing that I do with the flaw depth is I have a modification factor whenever I'm involved in stress corrosion cracking. And this is actually something that's quite unusual. I'm not aware that any of the other models will specifically look at that SCC crack shielding effect. Most of the time, the models will just assume that you've got a single crack, off you go, see what works. Those models will tend to be fairly conservative. And the reason for that is when you get SCC crack shielding, you actually have a lower stress intensity factor than you think you do. I've gone through kind of a calculation based on some classical solutions. And if you look at the math, the stress intensity factor that's associated with crack shielding is decreased by somewhere between about 10% and 30%.
Yeah, you mentioned SCC crack shielding. Just for those who don't know, can you explain what you mean by that a little bit?
Oh, sure. If you were to have a single crack in your pipe and say a single crack somewhere along the longitudinal seam weld, as you pressurize that crack, as you pressurize the pipeline, you're going to put a lot of stress into the walls of the pipeline. And if you've got a single crack, all of the stress intensity factor is really going to get concentrated on that one crack, right? So that's why cracks are a problem, because they've got such a stress intensity acting on them. But if you have a crack colony, an SCC crack colony, that means you've got multiple parallel cracks. They're typically about 1 millimeter or 2 millimeters apart. But what that means is all the stress in the pipe is not focused on one single individual crack. It's kind of dispersed amongst all the cracks in the colony. So it's kind of like all those cracks are sort of sharing the damage. Okay, and so I actually found some stress intensity factor solutions where somebody had figured out how much that would be. It's a classic book, Tata, Paris, and Irwin, which is just full of great stuff. But I realized from their work that your stress intensity factor is going to be decreased by somewhere between about 10% to 30%. And when you translate that into the K-squared, like we have in the equation, or if you're working with a J integral, that actually reduces things by between about 20% and 50%, which is huge, right? That's a big amount.
Yeah, I would say I've never seen a model sort of take into account like what you're saying in terms of SCC crack shielding. It's as if they treat each one separately, and then when you sum them up, it's almost like a disaster result every time.
Possibly, yeah. If you look at something like Corlas or the 𝐂𝐫𝐚𝐜 models, they really don't specify. They just say, what's the deepest crack, and off you go. I think if you look at something like API 579, I think that they actually, if my memory serves me, they say that if you have a bunch of cracks together, you should take the maximum depth, and then I think they add a correction factor on top of it in terms of depth. So they're actually getting even more conservative. So this is what I've done, and what I did is I said, if I can calculate what the effective stress intensity factor is, or the effective J is, in order to fit with my GEM model, I turn those correction factors into an equivalent depth. And so what I find is that I'm better off assuming that my crack is 63% as deep as it actually is, if I'm planning some sort of hydrotest program, or if I'm really worried about a service failure, then I would use a 0.84 depth correction factor. And these are really just, bumped on in front of the crack depth, just like the pi/4 is. For anybody that's interested, I've got a YouTube video, and it's called Pipeline Integrity SCC Shielding Factors, and I go through all the math. It's pretty complicated though, so I only suggest you do that if you're pretty hardcore into fraction mechanics. A little bit more fine print, nothing too serious. What I found is that if I want to do a metal loss calculation, I will basically split that remaining ligament to the gamma exponent, pull that off by itself, and just like 𝐴SME-B31G, I can use that just for a corrosion calculation, right? Which is kind of a bonus. I'm really sort of following along the original Battelle work. But what I found from the fraction mechanics derivation is, if I have metal loss, I'm going to limit that exponent to 1/2. And that's a very, very strange thing. And that, I'm sure that's going to cause some fracture experts all over the world all sorts of heartache. Because what it means is, as your corrosion flaw gets longer and longer, you're not converging to the remaining ligament as you would typically expect. You're actually converging to the square root of the remaining ligament. And that makes absolutely no sense at all. But that's what comes out of the mathematical derivation. And it seems to work with my validation so far. So I'm going to stick with that until I find a reason to change it. More fine print, the toughness that I use is the lower bound Wall&J correlation that you'll find in API 579. I've also needed to use some CTOD factors on some of my work here. So you can use the J integral equals M delta yield strength with M equals 2. That's a fairly standard equation where delta is your crack tip opening displacement. Now, a lot of people are really familiar with using the Sharpie over area correlation, or down in the US, it's like 12 Sharpie over area. I don't recommend that. And I've got some serious reasons for that. I'm not gonna bore you with that today, but when it comes to understanding how these models kind of developed, it kind of comes into play. It's very important to me, but that's kind of another subject to think about. I do have some circumferential flaws that I've tested. Those typically are under bending conditions. And so I've come up with a bending correction factor, which I'm still kind of working on. And I'll say right now that I've not been able to validate the gem for cold welds or grooving corrosion. I don't have clean and clear data to work with. But what I do have is a good pile of industry failure data. This turns out to be something like 300 data points. I've got laboratory machined cracks. I've got service cracks, fatigue, hooks. I've got stress corrosion cracks. I've got metal loss. In some cases, I've got full profiles. I've got circumferential cracks, and I've got through wall cracks for leak rupture boundary analysis. So I really have a long laundry list of all the cracks that we're potentially interested in. And what I've done is I can take all of those 300 flaws and apply it to the model I just showed you with all the little fine print applied. And what I find here is that in the great scheme of things line up really quite well. With the validation here on the y-axis, I've got the gem predicted failure strength. And on the x-axis, I've got the true measured failure strength. So ideally, all of my data points would fall along that diagonal line. And they're not perfect, but I've got a pretty good trend there. In some cases, I've got some data points that are higher than the line. And these are a problem because they're non-conservative, and that represents a safety issue, right? So you'll see a couple of purple diamonds up at the top. Those are axial cracks that are found in service. So those are, I can't tell from this, but they're either fatigue cracks or hook cracks. So that's not good. And there's a couple of reasons for that, one of which is variations in toughness in the material, one of which is you don't know the exact flaw shape. There are a few bits and pieces that could push them in the wrong direction. You can also look on the bottom side of the line, and you'll see a couple of green diamonds there, some purple diamonds, and some red squares. These represent overly conservative predictions. So these ones are good in that your pipeline is going to be safe, but if you have too many of those overly conservative predictions, your dig program could get quite expensive. There are some people out there that do model development and they basically strive to have a conservative model. I'm not one of those people. I really feel that if you've got a conservative model, but you've got no explanation as to why, that's really not good. You're just putting more uncertainty into your integrity program. So my goal is to get everything as accurate as possible. And once you've got everything accurate, that should give you a lot of confidence that the mathematics that are underlying what you're doing is good. So far I'm pretty pleased with this. Obviously, I like to play with data, and if anybody's got more, particularly SCC data that they want to send me, I would love to see that, because I've got so few data points. Now, if you look at the statistics here, I find that overall I have an accuracy of 1.04, which means that overall with these 300 data points, I'm on average about 4% overly conservative. And that's based on doing a failure ratio where I take each one of the 300 data points, I look at its true measured failure strength divided by its predicted failure strength, and then I just pool all those together and average them. So I come up with an average of 1.04 and a precision, so really just a standard deviation of 16. Now, if you compare that to several other models on the market, you're going to find that that's good. And I'm not aware of any other model or family of models or combination of models that anybody has ever sort of pooled everything together and gotten anything as consistent as this. Typically, people will do corrosion in one hand and they'll do cracking in the other hand, and then they'll separate out this and they'll separate out that, and they'll have 4 or 5 different models. Here, I'm trying to put everything together in one big sort of happy family of models that is really one model with a few little kind of tweaks on it. So I've done those statistics, and just one more slide I'll show you is I thought, is it fair to take these sort of 5 different groupings of flaws and put them all together? I mean, are they statistically reasonable to pool? And what I found is that I put those all together and I plot them as a normal curve, and they line up pretty darn well. Might be a little tricky to see, but I've got a normal curve that kind of floats through here. I don't get perfect agreement from the whole data set, but in the great scheme of things, I'm really pleased with the way that turned out. So,
yeah, I actually that was really thorough. I got nothing.
you're just back in your seat there, right?
Yeah, I enjoyed that. Wow, that was great.
Well, thank you. It's been a work in progress for a couple of years, and I've just been chipping away, and I've sort of tweaked things as they come along. So I'm pleased with the way the validation's going. Like I said, I don't have a lot of SCC data points, so I'm really keen to get some more of those.
Right. So are you working at all with a lab right now to do maybe like take you were talking about machining in some flaws and stuff. Have you actually done any taken pipe samples and done burst pressure tests yourself?
No. Right now, this is entirely a paper study. I'm an analyst. I'm not really a laboratory guy. If I did have a laboratory and have a whole pile of money, then sure, we could think of something like that. If you look at the various data that's available to industry, people have been doing these sorts of studies for 50 years. So, I can find the Battelle data from 1973, which is really a classic data set that all of the other analysts will study and use. It's kind of like the benchmark. In September of 2012, Kiefner and 𝐂𝐫𝐚𝐜𝐤𝐢𝐧𝐠 did an enormous report for PHMSA down in the United States, where they were looking at the PHMSA database of all the actual service failures. And they've got this fantastic 200-300 page document that goes through each one of the failures that they found and gives the lengths and gives the depths and gives you in some cases you get a micrograph of the fracture surface, and they'll say, well, here's the measured toughness and here's the measured yield strength. So that's been really a gold mine. As far as corrosion work goes, again, I found Battelle data from 1974. It's a little tricky to find. I also found there was a researcher named Dwayne Cronin, who's now a professor out east. And I found his doctoral thesis from 20 years ago, where he was doing a very detailed study on the B31G equations and R-string. And you can find his thesis online. So there's a fantastic 45 data sets and full profiles there to play with. Given that there is a lot of data out there to look at, I'm pretty happy with things, so far. I've managed to find almost 300 data points. Stress corrosion cracking is still a tricky one. The people that have those incidents don't necessarily want to advertise what's going on there.
It's always hard to get SCC pipe because nobody wants to share their dirty laundry.
Yeah. I did talk to one group that I know has just got a sweet pile of data, and they said they're not allowed to share the data unless they're involved in an industry recognized study. So that would mean either a PRCI study or a SEPA study or an API study or something like that. But I mean, I've got some papers here where I see all these plots, and I'm just itching to play with those numbers as well, but I can't.
Yeah, and honestly, you've been very thorough, very clear. I think it's looks like a great model, and I hope it develops even further. I just wanted to ask, I guess, you're talking about 𝐂𝐫𝐚𝐜 in the model, and then you were saying stay away from conducting sort of Sharpie values to try and get the toughness. As I'm sure you know very well, right now, I mean, just even 10 years ago, forget Sharpie toughness. No one even was talking about toughness, and people were just using tables, and it was kind of ignored. And I think in sort of recently, there's been a little bit more push, whether it's through convincing leadership teams to spend the money to go and take the cutout samples and actually do some material testing. So getting to, the ability to do Sharpie testing is a real step up for a lot of operators. What would you recommend when companies do their cutouts? Right now, a lot of people are doing Sharpie and thinking they're doing a great job. And as you and I know, there's a lot of issues with that, impact toughness versus real toughness and those different issues. But
yeah,
what would you recommend in terms of, okay, if we get cutouts, what types of tests should operators do to get 𝐂𝐫𝐚𝐜 values?
To be honest, I'm a believer in the keep it simple, stupid philosophy. So I don't have a problem with Sharpie. I know that it's sort of perceived to be amateur hour because you're just taking a sample and just going kablamo how much energy was in there. The reason that I mentioned not to use the Sharpie over area correlation earlier on is because I've got a really, really strong suspicion that the tests that were being done back at Fadhel 50 years ago, I believe they were probably being done under plain stress conditions. Okay, and the reason that I say that is if you read a report that came out of PRCI back in March of 2017, Dr. Ted Anderson. So he wrote a really interesting report, state-of-art review of crack models. And one of the things he recognized is that if you take the Sharpie over area correlation and you plot it against the J correlation or the Rolf-Novak correlation, maybe it was me that added the Rolf-Novak correlation. If you plot those three together, you'll find that Wallen and Rolf-Novak are pretty close to each other in terms of Sharpie versus like calculated J. But the Sharpie over area is just off the map by 10 times higher than the other two. And I don't recall seeing an explanation in the PRCI report that Ted Anderson had come up with, but it really struck him as being just, this is completely wacky. Why would that correlation be 10 times higher than the other two? So my suspicion is that perhaps those tests were done under plain stress conditions, which is not really appropriate for toughness. The toughness should always be done under plain strain conditions, right? Plain strain conditions makes it appear more brittle. Now, the reason that this comes into play is because the Fadhel group, the NG18 group back in the 1970s, the first thing that they did was their leak rupture boundary with a through-wall crack. A through-wall crack will be under plain stress conditions. So if you take a through-wall crack, you're coming up with a leak rupture boundary, you do all your tests, you correlate them to plain stress conditions, everything works out beautifully, right? So I think that that's what ended up happening, but I think nobody quite noticed that that was plain stress condition. And so that strip yield model that was used was just kind of plugged into the NG18 equation, and everybody thought it kind of sort of works. Now, where this becomes really interesting, and you really need to kind of flip your head around in all sorts of different directions, is if you look at the original log-secant model, hypothetically speaking, if you use the Sharpie over area correlation, and hypothetically, if I'm right, and it is high 10 times too high because of plane stress conditions, you would kind of expect somebody would notice that, right? You'd expect your model would go completely out the window. But when you look at the way that that model came together, they're also using a crack length in the place where they should be using a crack depth, right? Which means that their dimension is also off by probably 10 times. My suspicion is that what happens is the through-wall crack model was fine. Everybody was happy with it. They did this Frankenstein operation with NG18, and they said it kind of sort of works. But deep down, buried in the math, their toughness is 10 times too high, but their crack dimension that they're looking at, length versus depth, that's also 10 times too high. So those two errors actually cancel each other out, right? And so my suspicion is you've got two problems that are really deep down and dirty and buried hard in there, and nobody ever noticed it. Nobody ever recognized that there was a problem because it kind of sort of seemed to work. Now, when I do my model correlations here with GEM, I'm using those same Sharpie values, but I'm using the Wallen correlation. The other option I've got is to take Sharpie over area, assume that it's plane stress, and then do a correction factor to account for plane strain. And it lines up exactly the same way. I think that when you talk about cutouts and people doing all sorts of fancy stuff, I'm not necessarily sure that that's where you're going to gain a lot of advantage in your fracture mechanics models. Fracture mechanics is notorious for toughness value variation. If you look at the original Sharpie over area correlation, it's a shotgun blast. It's bad. So if you think about doing a cutout on your pipeline, that's going to cost you several $100,000 or millions of dollars, and you're going to cut a sample out that's that big, and you're going to send it off to the lab. Well, is that completely and utterly representative of your 100-kilometer pipeline? Probably not. It's a good start. It's a good guess.
Fair point. Yeah, yeah.
But is it really gonna give you that much benefit? I'm not so sure. I think it's of interest, sort of academically, and I know that the people that study fracture mechanics testing and they like their JR curves and stuff, and they like to set up their little crack tip opening displacements and stuff. It's all, to my mind, of academic interest. But when it comes to my sort of keep it simple, stupid philosophy, I think Sharpie surprisingly does quite a good job. Now, you can't just do one Sharpie test and say we're done. You want to do a whole rack of Sharpie tests, 8 or 10 or whatever. You might want to look at different temperatures to see if there's a transition, but I don't see that quick and easy sample is going to give you a substantially worse result than doing a full-on JR test. I think that you do those JR tests in the lab and you probably just end up with some sort of like analysis paralysis. You've got a whole other can of worms to think about.
Right.
If you're looking at something like API 579, you go to a level 2, they're going to want a JR curve, right? So that you can get your failure assessment diagram just absolutely perfect. Is fracture consistent enough across your 100-kilometer pipeline that single data point from that single $1 million cutout, is it worth it? I don't really think so.
Yeah, no, that's fair. That's fair. I mean, how many, to be statistically significant, you would need, on a 100-kilometer pipeline, you need so many cutouts, so many data points. I mean, you never really get there realistically, right?
I mean, if you look at a 100-kilometer pipeline, you might have different manufacturers along the pipeline, right? It could have been that this was built, your pipeline was built 50 years ago and there were 3 different manufacturers doing, different sections. And you've got to track down which one of those sections were by each manufacturer. And then you've got to do your 3 different cutouts. And then, okay, so now you've got 3 different answers. So now what do you do? It's,
Classic. Average them. No, I'm kidding.
Well, there's that old story of a person, a man with a clock knows what time it is, but a man with two clocks is never really sure what time it is.
Yeah, yeah,
Right.
yeah.
So here you've got a situation where it's easy enough to do a rack of Sharpies, see what you get. You know, averaging them, like you say, is dangerous because you might have just one really horrible sample that, you know, that pulls everything down. You might have one super fantastic sample that pulls everything up. It's a tricky game to play, but I think the nature of fracture mechanics is such that there's always scatter in the data, and that's, you know, unfortunately unavoidable. Some of the scatter is just due to, you know, you might have some fine precipitates in your material. You might have, I don't know, a bit of a lamination got into that sample somewhere. You might have some residual stresses. If you're cutting out a sample from a pipe that's maybe near the weld line, there are going to be residual stresses. You don't know how those residual stresses are going to relax once you cut out that sample. And if you've cut out a sample and you've relaxed residual stresses, is that really indicative of a crack that's still in the pipeline, that's still constrained? Not so much. I'm sure there are folks out there that are going to be keen on going into the detailed approach, and I can't say that that's wrong. It's just, for me, it's a bit of overkill.
Perfect. So I guess as our last point, you mentioned it a little bit, but what do you see going forward? What are your thoughts and your what's your anticipation for finalizing or building this model further?
Well, with this model, I've pretty much gone as far as I can based on the data that I've got. I'm certainly open to other industry data that I find along the way and incorporating it in and seeing if any of my statistics change. You know, for me, this was a model that I started working on a couple of years ago, and it's sort of evolved, and there was some good stuff and some bad stuff, and I kind of worked for the last couple of years. I think we talked yesterday that I was working with a consulting company that kind of had some trouble with the oil and gas business kind of going downhill at the end of last year, and then COVID hit. So I was let go. So what that means is I don't really have a platform other than myself to promote the model. So what I'm doing is I've got the model to where it is. I've put together a series of YouTube videos. The ones that basically look at model validation, they're just called Pipeline Integrity, Gamma Exponent Model Validation, parts 1 to 6. And then the sections where I question the theory from the NG18 model, those are called Pipeline Integrity, Things That Make Me Go, And so I've kind of got these two series out. I'm trying to promote them on LinkedIn and really getting people like you to sort of stop and think and go, hey, wow, you know, length and depth, that's kind of an important thing to differentiate. And if I can get enough people in the business that scratch their heads and say, well, we shouldn't be working with length. We shouldn't be happy with models that are overly conservative by 20, 30%. You know, we need to think about what's technically correct. And here, if you've got an improved accuracy in your model, I mean, that's potentially worth hundreds of millions of dollars to some of the bigger operators. So I'm at a point right now where I'm just trying to spread the conversation, do my videos, talk to people like you. I'm hoping to talk to a NACE group in the next couple of weeks and just kind of get people thinking about things and start some conversations. And where things go from there really depends on me having this information land on the right desks of people that can make a difference. So, you know.
Right. So have you published a paper in a journal that we can share in the link below, or have you sort of put the GEM model together?
I've got a mathematical, fully complete, detailed derivation that's in the ASME Journal of Pressure Vessel Technology. I basically have a list of references at the end of each one of my videos. So it's ASME Journal of Pressure Vessel Technology number 19-1190. And it's called A Reconsideration of the 𝐂𝐫𝐚𝐜 Model for Pipelines. And that goes through all the mathematics of the derivation. And it starts off with a simple validation. So that's one thing. A second thing is I've got an ASME Pressure Vessels and Piping virtual conference paper. So that virtual conference is actually on right now. And anybody that's taking part in that conference can jump into the list of papers and they can look for ASME, pressure vessels and piping, gamma exponent validation. And that's where I go through a lot of the crack work, where I look at the Battelle cracks, the axial stress corrosion cracks, I look at the fatigue cracks, I look at the hook cracks, I look at all of those. So that's been published. And then I also have a NACE paper from the Regina conference earlier this year, where I go through the corrosion side of things. So I've got some papers in play, I've got some conversations in play, I've got some videos in play. I'm just trying to kind of get people thinking about this sort of thing, and hopefully, you know, a director of some company or a key research person or somebody with gray hairs will say, hey, you know, we should be trying that a little more on that. So that's where I am.
Perfect. So if people want to reach out to you, you mentioned you have the YouTube series, which we'll link in the link below. What's your, if you don't mind sharing your contact information and how people can reach out to you if they want to learn more about the GEM model?
Sure. If you go to YouTube and just look up Colin Scott Pipeline Integrity, things that make me go, or gamma exponent validation, you'll pop up with a whole series of videos. Each one is between about 10 and 15 minutes, so help yourself to those. At the end of each of those, I say, if you want to contact me, I'm happy to be contacted through LinkedIn. It's probably sort of the most convenient. I try and check on that every couple of times a week just to see what's going on. So send me a contact message. Please try write something in the message saying, I have a question about GEM, because you know what LinkedIn is, where you just get random people that are just trying to sell something. So, you know, please contact me and say, I have a GEM question, I don't understand this, or tell me more about this data, or I don't understand the theory. I'm good with that, and I'm checking it every couple of days. So you know, I'll try and respond fairly regularly.
Excellent. Well, as part of the post, we're going to put your contact to your LinkedIn page, and I encourage everybody to check out Colin Scott's YouTube videos, as well as go check out his LinkedIn page, send him a connection request. Make sure you put a message in about wanting to learn more about the GEM model. And Colin, thank you so much for coming on the show. This is part 2 of the Cracking in the World of Pipeline series. And, you know, so much information. Thank you so much for coming on.
Thank you very much to you, Hussain. I appreciate having the chance to talk about this. It's always good to find other people in the business that that want to discuss these sorts of things. And I particularly appreciate you you arranging this talk where I can really advertise my GEM model. I'm keen on it. Hopefully, people will pick up on it, and we'll go from there. So thank you very much, and I'll make sure to keep an eye out for some of your other visitors and see what sorts of interesting things they have to say. Thank you.
Perfect. Thank you so much. Take care then. Hey everybody, welcome back. Hope you enjoyed that interview. Please remember to like, subscribe, and share. And until next time, keep on pigging, digging, repair-a-coating, and backfilling. Take care.